So let's look what happens at the relativistic limit. If this sounds far-fetched, it isn't. In fact, most white dwarfs are already in the relativistic limit. Let's check that. If you pack the electrons close together, the velocities they're going to have by the uncertainty principle are. So substitute the delta x by the number density. That's a measurement of volume. So you can write that the cube of their momentum is equal to the cube of the Planck constant times the number density, the electron number density. So if you solve for the velocity is the Planck constant over the mass times the cubic root of the electron number density. And the number density is the density over the mean molecular weight times the atomic mass unit for singly ionized species. Now, for the typical white dwarf, you have a mass of about 1 solar mass and a radius of about 10,000 kilometers. If you substitute these values, you find that the velocity of the electrons inside of the white dwarf is about 35% of the speed of light. So the electrons are moving at the relativistic velocities, and you need to use the relativistic equation of state for degenerate matter. Now, for relativistic degenerate matter, the equation of state changes slightly from the pressure being proportional to the density to the power of 5/3 to the density to the power of 4/3. Equating this again to the pressure that we found for the core of the white dwarf, and if again we solve for the radius, we have now a relationship between the cube of the radius and the inverse of the volume, not the 6th power of the radius and the inverse of the volume. If we substitute the density for the mass, this yields, look what's happening here. You have the cube of the radius both on the left-hand side and the right-hand side. So you can cancel them. And if you solve for the mass, there are only constants on the right-hand side. That means that there is only one single mass that an ultra-relativistic white dwarf can have. If you work out the numbers, this gives you about 1.44 solar mass. This is the Chandrasekhar limit. This is a very curious result. Because the radius cancel out in this equation, there seems to be only one mass that a fully relativistic white dwarf can have. This is understood as a mass limit. As one adds more and more mass, the white dwarf shrinks to produce more pressure. Using the non-relativistic equation of state, a volume of 0 would only be achieved at infinite mass. That is the curve here, the blue curve for a non-relativistic equation of state. Now that's because the non-relativistic equation of state assumes that the electrons can move faster than the speed of light, producing ever more pressure as they get squeezed together. Yet physically, as electrons approach the speed limit, which is the speed of light, increasingly more energy is required to increase their velocity. A partially relativistic white dwarf has a smaller radius than the non-relativistic one. So the green one is the one that is the curve that you get for the relativistic Fermi gas. As you see, for the same mass, partially relativistic white dwarf has a smaller radius. That's the relativistic correction because you need to add more energy to increase the velocity. Now, eventually, a volume 0 is reached for the mass given by the Chandrasekhar limit. That's the red dotted line here, the ultra-relativistic limit or the Chandrasekhar limit. This mass limit sets the maximum mass that a white dwarf can have.